Okay, in this tutorial we're going to be looking at polynomial equations. Okay, so we start by thinking about our quadratic equations. So we're going to think about quadratic equations. Okay, so we're saying that we've got a z squared plus b z plus c equaling 0. Okay, so we're saying that a, b and c are all real. Okay, then the roots depend upon the discriminant. Okay, so remember the discriminant, okay, is equal to b squared take 4ac. Okay, and remember if the discriminant is bigger than 0, okay, then we have two distinct real roots, okay, or real factors. Okay, if our discriminant equals 0, then we have one real root, and if our discriminant is less than 0, then we have one pair of complex conjugate roots. Okay, so I've spoken about that previously. Okay, but what we do is there's a relationship between the roots and the coefficient. Okay, so if we're starting with our quadratic up here, okay, our a z squared plus b of z plus c equals 0. Okay, if we're starting off with that, okay, then really what we can say is we could divide all this by a, so we get that, okay, just so that we don't have a coefficient in front of our z squared. Okay, so if we're going to do that, okay, then what we could say is we could factorise that. Okay, and get two roots, alpha and beta. Okay, we're just saying that we've got alpha and beta. Now if we were to expand that back out though, okay, then what we get is z squared minus alpha plus beta z, okay, plus alpha times beta equaling 0. Just if we were to expand that out. Okay, so basically what we're saying is this bit, okay, is the sum of the roots, because we're saying that these were our roots, okay, and these are the product of our roots. Okay, and so we're saying, well, then alpha plus beta equals our b divided by a, okay, and that our alpha times beta, okay, is equal to our c divided by a. Okay, so it's using that information, okay, it can work quite well because this provides a relationship between the roots, okay, that we had and our coefficients. Okay, so we had our coefficients up here, okay, these are our roots, okay, so we end up with that link between them. Okay, so rather than solving quadratic equations, consider the reverse problem of forming a quadratic equation with real coefficients given one of the roots. Okay, so we're going to be looking at our first worked example. Okay, so we want to find the equation of the quadratic p of z, okay, given that p of minus 2 plus 5i equals 0. Okay, so what we're doing is we're saying, well, alpha is equal to minus 2 plus 5i. Okay, and so remember we're talking about, these are our situations where we've got a pair of conjugate roots. Okay, so there's one part that I probably didn't put in over here, and really that for alpha, well then alpha bar is equal to beta. Okay, so up here we have alpha being minus 2 plus 5i, okay, then beta equals minus 2 take 5i. Okay, so remembering now that alpha and beta, when we add them together, okay, well, when we add our conjugate roots, our complex part disappears, so we just add these together to give us minus 4. Okay, and our alpha times beta, okay, well that's going to be our minus 2 plus 5i, and our minus 2 take 5i. Okay, so when we expand that out, we're going to get positive 4, okay, from this times that. Then we're going to get positive 10i take 10i take 25i squared. So we're going to get 4 take 25i squared. Okay, I squared is negative 1, so we make that 4 plus 25, which gives us 29. Okay, so then what we can do then is put it all together, okay, because we know now all our information up here. Okay, so we've got then that P of Z has to equal our Z squared. Okay, take our alpha plus beta, well, so take away our negative 4, okay, Z plus our alpha times beta. So all up we're going to be Z squared take 4Z plus 29. Okay, so we start off with just knowing a single root, and from there we're able to find out what the polynomial, or what our quadratic in this case, need to be. Okay, so we'll flick over. Okay, so now we'll look at solving cubic equations. So, when we've got our cubic equations, they're going to be in the form az cubed plus bz squared plus c of z plus d equaling 0. Okay, and with this, we have 3 distinct real roots, which is the examples that we've seen previously. Okay, or you can have 1 real root and a pair of conjugate roots. Okay, so we'll look at how to go about solving these ones. So we'll look at work example 19, which is if we've got z cubed plus 2z squared plus 21z minus 58 equaling 0, and we're going to find all our roots. Okay, so the first thing we need to do is actually find a factor. Okay, so what we do is we sub in a lot of values here. Okay, and when we do that, we find that when we sub in 2 into that, okay, then it does equal 0. Okay, so that means that z minus 2 is a factor. Okay, because remember we've got to change our sign. So when we sub in and find that positive 2 gives us 0, well then it means z minus 2 is a factor. Now we need to get rid of that factor out of here. Okay, so in the textbook it just says use short division. Well, we haven't really talked about that at all. So we're going to look at long division. Okay, and then we're going to look at synthetic division, which does the same thing but a fair bit quicker. So we need to set this up with z minus 2 going into our z cubed plus 2z squared plus 21z minus 58. Okay, so we go, how many z's in z cubed? Well, that is z squared. We multiply back around. So z squared times z gives us z cubed. Z squared times negative 2 gives us negative 2z squared. Put that inside brackets. Take away sign. So it goes z cubed take z cubed gives us 0. 2z squared take negative 2z squared gives us 4z squared. Then bring everything else down. Plus 21z minus 58. Okay, now we go again. How many z's in 4z squared? Well, that is 4z. Multiply back through gives us 4z squared. Take 8z. Put in brackets. Take away. Line underneath. Okay, 4z squared take 4z squared is 0. 21z take negative 8z gives us 29z. Okay, and bring down our minus 58. Okay, how many z's in 29z? Well, there's 29 of them. Multiply back through, we get 29z. Okay, minus 58. Take away, and as we'd expect, that gives us 0. Okay, so we find our factor here. Okay, what's left over? So we can say that we have now z take 2 outside of z squared plus 4z plus 29. Okay, so I'm going to show you another way which will give us the same answer. It's called synthetic division. Okay, and what we do is we write down our coefficients, okay, of our numbers here. Okay, so we've got 1, 2, 21 and minus 58. Okay, and what we do is just up here, okay, is we put in our number that we originally subbed in here. Okay, or we change the sign here. So actually put in our 2. Okay, now what we do is first of all is this first number comes straight down, our 1. Now what we do is we go 2 times 1 gives us 2, then 2 plus 2 gives us 4. Then we do 2 times 4 gives us 8. 21 plus 8 gives us 29. Okay, 2 times 29 gives us 58. Okay, add them together, we get 0. Okay, and these gives us our coefficient of a degree lower. So this gives us our z squared plus 4z plus 29. Exactly like we had here. Okay, this one here, okay, is our remainder. Okay, which for these ones is always 0. That's what we want. Okay, so you can see just a little bit of a different way to do it. It's called synthetic division, and you can see it's a little bit clearer and less complicated than our long division of polynomials. Okay, so now we just need to find our factors of this. Okay, here. Okay, we know it's not going to be very nice. Okay, so we may as well go straight for our general quadratic formula. Okay, it's actually the same as an example we did previously. Okay, and that's what the worked example says, to just look at that, but I think that's a little bit of a waste. So remember our general quadratic formula, negative b plus or minus square root of b squared, take 4ac over 2a. So we'll sub in our numbers. So negative 4 plus or minus square root of 4 squared, take 4 times 1 times 29 over 2 times 1. Okay, so we get here, okay, that we've gotten our negative 4 plus or minus square root of 16, take 4 times 29, it's going to be 117. So if I don't muck that up. Okay, 117. Yep, over 2. Okay, which means we're at negative 4. So plus or minus square root of negative 101. Okay, not looking very nice here. Over 2. Okay, let me just double check our 4 times 29 here actually, to make sure I'm okay there. I know we're 116, that makes more sense. So 116, which means we're square root of negative 100. Okay, that's a little bit nicer. Okay, because that gives us negative 4 plus or minus 2 root negative 25 over 2. Okay, helps us out a fair bit. Okay, and then we can divide by our 2's for a start. So we're at -2 plus or minus root of -25. So -2 plus or minus 5i. Okay, which is what we end up with our answer. Okay, so in the end we have our, sorry I'm looking on the wrong page. Okay, so our roots are z equals 2, okay, or z equals our -2 plus or minus 5i. Okay, so just make sure we get our arithmetic right there. Okay, so we'll keep moving on. Okay, so we talk about the conjugate root theorem. So our previous two results are true not only for quadratic and cubic equations, but for any nth degree polynomial. In general, provided that all the coefficients of the polynomial are real, if the roots are complex, they must occur in conjugate pairs. Right. Note that if one of the coefficients is a complex number, then the roots do not occur in conjugate pairs. Rather than formulating a problem such as solving a cubic equation, consider the reverse problem. Determine some of the coefficients of a cubic equation with real coefficients given one of the roots. Okay, so basically what we're saying is that if all our coefficients are real, okay, and if the roots are complex, then the roots have to be in conjugate pairs. Okay, but if not all of our coefficients are real, then that goes out the window. Okay, so what we've got now is we've got the polynomial pz equals z cubed plus bz squared plus c of z take 75 equals 0. Okay, we know b and c are real, and we also know that p of -4 plus 3i equals 0. Okay, and we've got to find the values of b and c and state all the roots for this equaling 0. Okay, so first of all, we need to go, well, let's say that our alpha is our -4 plus 3i. Okay, then remember our beta is our conjugate, so it's -4 take 3i. Okay, then our alpha plus our beta equals -8. Okay, because we just add these two, and then our alpha times our beta. Okay, well, all it is, remember, is it's going to be this squared and that squared, or sorry, this times this and that times that, so we're 16, okay, take 9i squared, and so it's 16 plus 9, so we're 25. Okay, so we know then that we've got a quadratic factor, okay, that is going to be z squared plus 8z plus 25. Okay, because remembering that we take away this value, okay, so it ends up being positive 8. Okay, so then we're looking at using some division again, okay, because we need to divide this into here. Okay, so what we do is we go, okay, well, we've got our no, just double checking here. No, sorry, we just need to find our other factor, okay, for this one. So just think here, okay, well, we know we need another z, that's a given, okay, and our other number, when multiplied by our constant here, has to give -75, so we can see that our other factor has to be z minus 3 for this one. Okay, so now we're going to expand our brackets, which is going to give us z cubed plus 8z squared plus 25z minus 3z squared take 24z take 75, okay, equaling 0. So when we simplify that, we get z cubed plus 5z squared plus z take 75 equals 0. Okay, so we can see then that b has to equal 5 then. Okay, and that c is equal to 1. Okay, but we haven't quite finished yet. We're almost there. Okay, because we need to state what our roots are. So our roots are z equals 3 from here. Okay, and we also know them from up here. Okay, there's got to also be and z equals minus 4 plus or minus 3i. Okay, to take into account our complex conjugate pair. Okay, so we're getting there. So cubic equations with complex coefficients. We can use the grouping technique to solve certain types of cubic equations with complex coefficients. So this time we're going to solve for z if we have z cubed plus iz squared plus 5z plus 5i equaling 0. Okay, so what we're doing here is, what we're doing is we're taking out z squared as a common factor. So we're going z squared, and then we're left with z plus I. Okay, and over here, we're going to take out 5 as a common factor. So we're again left with z plus I. So we're doing this grouping idea. Okay, so that means then that we can bring these together and say that we've got z squared plus 5 and z plus I equaling 0. Sorry, equaling 0. Okay, so here we can say, well, that one's going to be z squared, take 5i squared. This is going to be z plus I. Okay, and it's just so that way we can make this as z plus square root of 5i. Sorry, square root of 5i, and z minus square root of 5i. Z plus I. Okay, because difference between two squares. Okay, so then we can simplify that and say, okay, so we're saying that z then equals plus or minus square root of 5i, or z equals negative I from our null factor law. Okay, so general cubic equations. So our next little section. Okay, if one of the roots of a cubic equation is given, the remaining roots can be determined. Okay, note that if one of the coefficients in the cubic equation is a complex number, the roots do not all occur in conjugate pairs. Okay, so this one we're showing that z equals 5 take 2i. Okay, is a root of the equation z cubed plus minus 5 plus 2i z squared plus 4z plus 8i minus 20 equals 0. Okay, and hence find all the roots. Okay, so what we're going to do is we're going to sub in this value for z. Okay, so we end up with our 5 minus 2i cubed plus minus 5 plus 2i times 5 minus 2i squared plus 4 times 5 minus 2i plus 8i minus 20 equals 0. Okay, then we're going to simplify that. Okay, down a fair bit. Okay, so we've got this. Okay, so we're going to simplify that, say that we've got 5 minus 2i cubed minus 5 take 2i cubed plus 20 take 8i plus 8i minus 20 equals 0. Okay, so since it equals 0, then we know it's a it is actually a factor. Okay, since that all disappears. Okay, which is nice there. Okay, so now that we know that that's a factor, okay, what we can do is we see that we get z minus 5 plus 2i. Okay, and z squared plus 4 equaling 0. Okay, we're going to do this as our difference between two squares. Do z take 4i squared. Okay, and then, okay, so this comes from the fact that we knew that we had a root there. Okay, so then our roots become, as we know, z equals 5 take 2i. Okay, and that we also get that z equals plus or minus 2i. Okay, just from taking the square of that. Okay, so getting there, we're almost finished. Okay, so the fundamental theorem of algebra. Okay, this theorem states that an nth degree polynomial will always have exactly n roots, provided that multiple roots are counted accordingly. Okay, so our quadratic equations with real coefficients. Okay, so we need to talk quartics now. Okay, so we're saying that we've got p of z is a z to the 4 plus b z cubed plus c z squared plus d of z plus e. Okay, with all real coefficients. Okay, so this can have four linear factors. The roots can either be all real roots, two real roots, and one pair of complex conjugate roots, or two pairs of complex conjugate roots. So because we've got the four roots, okay, we can have all four real, we can have two real, two complex conjugates, or we can have two pairs of complex conjugates. Okay, so we're going to look at worked example 23. Okay, we're saying that if we've got to solve for z, if z to the power of 4 plus 3z squared plus 28 equals 0. Okay, so what we do for this one is we're going to use the substitution that u equals z squared. So this means that this becomes u squared plus 3u take 28 equaling 0. Okay, it's always a nice one to do there. Then we can factorise that. Okay, and we're going to get u plus 7, u take 4. Okay, put our u equals z squared back in. That means that we get z squared plus 7 and z squared take 4 equaling 0. Okay, so then we can go difference between two squares makes it z squared take 7i squared. Okay, and we've still got our z squared take 4 equaling 0. So that means that we get z plus 7i, sorry, root 7i, z take root 7i, z plus 2, and z take 2, equaling our factors. Okay, so, sorry, is our expansion, so our factors therefore from our null factor law is z equals plus or minus root 7i, or z equals plus or minus 2. Okay, so we've got one last worked example to finish off, okay, which is solving quadratic equations with real coefficients. So solving a general quadratic is more difficult. Okay, to make it easier, one of the roots can be given. However, this makes it too easy, so one of the coefficients will be an unknown real number. So we've got given that 3 take 2i is a root to the equation z to the 4 take 6z cubed plus 18z squared plus p of z plus 65 equals 0. Okay, find all the roots and the real number p. Okay, so let's start off with by saying that alpha equals our 3 take 2i. Okay, that means our beta is going to equal our 3 plus 2i. Okay, so that means our alpha plus our beta equals 6, and our alpha times our beta equals our 9 take 4i squared, okay, which is going to equal 13. Okay, so we know then that z squared take 6z plus 13 is a factor. Okay, so we know that's a factor. Okay, so what we can do now is we can do our division of polynomials. So we can do z squared take 6z plus 13 into our z to the 4 take 6z cubed plus 18z squared plus pz plus 65. Okay, so what we do is we go, well, how many z squareds in z to the 4? Well, there's z squared of them, multiply back through, get z to the 4, take 6z cubed plus 13z squared. Okay, take it away. Okay, this one goes, we're left with 5z squared plus pz plus 65. Okay, we go, how many z squareds in 5z squared? Well, that gives us 5. Multiplied back through gives us 5z squared. Take 30z plus 65. Now we know when we take this away, this has to equal 0 because we know that this is a factor. Okay, so we can see here, well, this gives us 0, this gives us 0. Okay, this is going to give us 0. Okay, then it means that p, okay, has to be our negative 30. So we can say p equals negative 30 from there. Now that's a little bit different to how they do it in the textbook. Okay, but we get our p equals negative 30 from there. Okay, so that means then that we've got z to the 4 take 6z cubed plus 18z squared take 30z plus 65 equaling 0. Okay, and so we know then, okay, that we've got our factors up here. Okay, so we know these are two of our factors. Okay, that z equals 3 plus or minus 2i. Okay, and we go, well, what are our other factors? Well, actually, we know it up here. Okay, because we know that this is what was left. Okay, so we know that we also have our z plus 5, sorry, our z squared plus 5, make that z squared, take 5i squared. Okay, so that means that we're going to get z take root 5i and z plus root 5i. So our remaining two factors are z equals plus or minus root 5i. Okay, so that's a little bit different to the way they go about in the book. End up being a reasonably long section. Okay, fair few worked examples in there and a bit to get your head around. Hopefully that gets you through the questions though.